Okay. So if all goes well, you should be seeing my first slide. Are you seeing it? I'm seeing it on my side.
Yes.
Okay. So I wanted to also say a few things about this team, the tutor group. As in any sport, there are 11 people. So you can think of this as the ICTS 11. And like IPL, they're allowed to have overseas players. So 3 of the 11 are from the Azim Premji University, undergraduates like all of you. Okay. And they would be able to tell you that I am very fond of puns. So you have one in the title itself. Don't take optics lightly. And I thought there's a very interesting way of seeing from some historical developments, giving you evidence that optics is really a terribly important subject. I mean, this is in a somewhat lighter vein. Okay. So if you want to study, ask any expert, they will tell you, study a book on optics by Born and Wolf. Okay. So when I started my studies, I also wanted to study Born and Wolf. I went to my thesis supervisor and he told me, actually, Born and Wolf is not a very user-friendly book. There was a much nicer book written by Born himself, right? In German, Max Born, a Nobel Prize-winning physicist whose name you would have heard. And he said, now what's the proof that this is a really good book? Now, if your friends say that your book is good, that doesn't mean anything. But I'll show you that actually the enemies said that his book was really good. So I bought myself a copy many years later, and I'm just showing you. So here's the title in German, author, and here you should have seen the name of the German publisher, Springer. But what you actually see is photo lithograph reproduction by some Edwards and Company in the United States. That means they basically pirated the book. And why have they pirated the book? Published and distributed in the public interest by the authority of the alien property custodian under license number. So in the middle of World War II, 1943, America decided that this book in German is in the public interest, so they pirated it and published it. So that's a high praise indeed, okay? But there are many practical reasons. We all know about telescopes and microscopes, part of the school and college curriculum. And fundamentally, they allow us to explore the very large and the very small. Okay? But that's a very old theme, 1600s. Of course, the telescopes and microscope improved, but in the first half of the 20th century, something remarkable happened. Optical principle of diffraction, as applied to X-rays, allowed scientists to explore the atomic and molecular structure of matter. So what it really means is today you go to Wikipedia and you just type in anything, some ribonuclease, some enzyme, and you will get a diagram telling you exactly which atom is sitting where. And these were made by a remarkable technique called X-ray crystallography. And then if we come to and that's continued, of course. If we come to the latter half of the 20th century, a dramatic improvement occurred in telescopes in their ability to show fine details. And this had to do, again, with a very basic optical principle, Young's double slit experiment. Okay, I'll be telling you more about this much later in the course. But at this stage, I thought I'd make the point that these very basic textbook things in optics, diffraction, interference, played a fundamental role in telling us, on the one hand, where atoms lie in matter, and what is happening in these remote astronomical objects. Okay. Plus, especially in the 21st century, if you said that the 20th century was the century of the electron, the 21st century is the century of the photon. All of you are seeing whatever you're seeing by light traveling on optical fibers. And if you just take a simple thing like timekeeping, the most accurate clocks are based on optics and atomic physics. And the rate of these clocks is pretty amazing. They would gain or lose 1 second in the age of the universe. I mean, that sounds unbelievable, right? I won't be able to reach that topic, but I will certainly like to, yes. The last line was about solar energy, which we'll come back to. So a little bit about X-ray crystallography. So I have just picked one molecule, right? I hope you can see it down below. It's called collagen. You see three chains, protein chains winding around each other. It's called the triple helix. Okay, collagen is in your hair, in your nails. It's a biological molecule, not as famous as DNA. And the reason why I have picked this molecule is that its triple helical structure was unraveled in the city of Chennai. Maybe a little bit of patriotism because I was kind of brought up there. By Indian scientists. So here is a name which should be very famous, G.N. Ramchandran. And here is his fellow adventurer, his student at that time, Gopinath Kartha, right? And they, with very basic equipment and very limited computer facilities, and of course, brilliant insight into the chemistry, did this structure. Okay, it's just an example with an Indian connection of X-ray crystallography in action. Of course, both Ramchandran and Kartha went on to do many, many more things in this field. And now let me fast forward to something, another molecule, I mean, which is gigantic. The one on the left is what I call a ribosome, which is the kind of complicated machine inside everyone's cell, which takes in messages from DNA, which are carried by RNA and then gathers amino acids and stitches them into proteins. Don't ask me how, I'm only a physicist. Okay? And the second structure shows how this ribosome looks when it is in action. Okay? So this is a fantastic achievement of 21st century X-ray crystallography. Okay? And here are the three people who won the 2009 Nobel Prize for that, one of whom is of Indian origin. Okay? So I just thought, just to tell you that optical principles have played a fantastic role in telling us the structure of matter, even in very complicated forms. And, now, again, a very brief introduction, a preview of what we will do much later in the course is what is called interferometric imaging. Now, normal imaging is where you point a telescope to something and you take a picture, so to speak. But interferometric imaging is when you have multiple telescopes and you combine the light from these telescopes or radio waves from these telescopes, and you do something like Young's interference. Okay. So I'll again give you an Indian example and an international example. And just like the Indian example had a bit of bias from my city of Chennai, this also has some bias because it's taken from work done recently at the National Center for Radio Astrophysics, NCRA, and you heard that I worked there for a decade. And it's a sister institute of ICTS, part of the TIFR family. It doesn't look like a very interesting picture. It's a picture of the planet Venus. And by the way, the telescope is, and it makes many more interesting looking pictures than this. But I had a specific reason for choosing this picture. Actually, the tools of astronomy are defied by Venus because it's covered by cloud, but radio waves come through. And this is at long wavelengths. You're not only seeing the surface of Venus, but even looking below. Okay? So there's a lot of interesting physics in these pictures, which you can find out. But the real reason for picking this is that at the age of 90, the founder of this institution and this telescope, Professor Govind, is actually an author on this paper. And I remember when I was in NCRA, he kept telling everyone, you should look at Venus. And he's not only the father of radio astronomy, his students went on to work on UT telescope, JMRT. Then their students came. And I think he's now the great-grandfather of Indian radio astronomy. The other authors on this paper are his student's student and his student's student's student. Okay. So that's a little bit about interferometric imaging. And this is a picture that all of you must have seen. It went viral. Actually, it looks a bit like the previous picture, but something wrong. But it's a fantastic achievement of peering into the heart of a galaxy called M87 and seeing a ring of radio waves at millimeter wavelengths, which have just missed a black hole. Now that is completely mind-blowing. Okay, and this again is the 21st century achievement. It didn't win a Nobel Prize yet, but did win something called the Fundamental Physics Prize, which is $3 million. So I should be showing you a picture of the people behind it, except that there are 347 authors, right? So each of whom got around $8,000. And in fact, 6 of them are good friends of mine. So I have just picked 2 of the authors who kind of led the project and saw it through these decades. Shepard Dollerman on one side of the Atlantic Ocean, and Harvard and MIT and so on, and the other is Heino Falke. Okay, so this is just to tell you that optical principles played a fundamental role in astronomy in the 20th century. Now, all of you know what the T in ICTS stands for. It's a Center of Theoretical Sciences. So apart from all these practical reasons, I have to give you some theoretical reasons why one should. So I will be starting with this thing called Fermat's principle of least time. We'll be spending quite a bit of time, a long time on it. But it is also a model for something more advanced, which you usually learn only in MSc, which applies not just to light, but applies to all kinds of mechanical systems. It's called the principle of least action. Okay, so that's a good theoretical reason to study optics, not in this, high school form of just tracing rays, but in this more sophisticated form of asking which are the rays which travel in the least time. Then you go to wave optics, which again you see in high school and in college, but perhaps they don't reach the stage where the wave optics becomes a very good preparation for the mathematics of quantum physics, and we will try to reach that stage. And moving on to mathematics, it's interesting that Fermat himself was an outstanding mathematician, and in the late 19th, early 20th century, Poincaré was one of the outstanding mathematicians, and they took interest in optics. Poincaré spent entire 2 semesters giving lectures on optics, and again, a little bit of bias. I worked at the Raman Research Institute, and long before I joined it, one of the remarkable research students there called Pancharatnam discovered a very interesting mathematical and physical phenomenon concerning wave optics. So again, wave optics you would have thought was dead in 1955, but no, there were interesting things to be found. But we are going to begin with geometrical optics. And many of you may have suffered trying to remember sign convention, U, V, tracing rays. Typically you trace 2 rays, so wherever they intersect is the image. Extremely boring. But I want to now make the point that geometrical optics has given surprises well into the 20th century. Okay, and I have 2 examples on the next slide. Okay, so this is a picture taken with the Hubble Space Telescope. It's a single telescope. It doesn't use interferometry, but it's got a very good resolving power. It's looking at a very distant cluster of galaxies. So each one of these, perhaps this one, is a galaxy like our own, 100,000 light years in size, and they are clustered. They are moving around in a common gravitational field. Okay, so that's fine. Clusters of galaxies have been known from the early 20th century. But what is this, right? And if you look carefully, you see something pretty strange here. No one has seen a galaxy looking like this. So sometime in the middle 1970s, a couple of astronomers started seeing these strange arcs in their pictures, and they had no clue as to what it was. Okay, these were astronomers on the west coast of the United States, so they would keep it in that drawer, and whenever they had a visitor, they would show him the picture and say, "Hey, look at this weird picture." Okay, and then some astronomers in France, of course, they kept it; they didn't publicize it. Some astronomers in France decided independently, found these arcs in different systems, and when they published, very quickly people realized that this is an optical phenomenon. This is something called a gravitational lens. So this galaxy is not at the cluster, it's way behind. And the light from that galaxy is passing this cluster, being bent by gravity, and bent in such a way that what would normally have been a small image like this has got magnified into an arc. So the magnification is only in one direction. Okay. Now this is a remarkable phenomenon. The optics is interesting, the astronomy is interesting. Tells you about the mass of the cluster, tells you about the galaxy behind. But for today's overview, the main point to make is that the optics of gravitational lensing, and that's a subject I've worked on a little bit, and naturally having a bias, I will tell you more about it, was really uncovered, clarified only, in the 20th century. Right? And the other example, which I very much like, because I mean, you have to guess what this is. So the place is Mongolia. Okay, so this is a desolate part of Mongolia, and winter is very cold. So naturally, you would like to gather solar energy and convert it into hot water or electricity. So they have all these reflectors, right, which gather the solar energy and focus it onto pipes which are sitting here, and they get hot water. And believe me, if you lived in Mongolia, you would want to bathe in hot water. Okay. However, look at the slightly weird shape of these collectors, right? Normally, if you wanted to focus sunlight, you might use a sphere. Some of you might think, no, you can use a parabola, but I can assure you that this is not a sphere and not a parabola. So again, as late as 1960s, okay, a scientist called Winston in the University of Chicago thought about a problem, saying, look, I don't want to form the image of something. I have an object of a finite area. I want to focus it on a detector or something else, maybe a piece of food to be cooked, which also has a finite area. And that's a different problem in optics, right? We will be talking about that problem. So these are not focusers, they are called concentrators. And today, if you want a very efficient collection of solar energy, you will use concentrators. You will not use focusing. Again, it's something that you will appreciate when we come to it 3 or 4 lectures from now. So just to tell you that geometrical optics is also not dead and is very interesting. Okay, so now we come to Fermat. So let's look at Fermat himself. He looks like a man of principle. In fact, he looks very serious. Even today, may say he looks like a lawyer or a judge, right? Because this is taken in some 1620 or something, painted. That's what he looks like. Well, the answer is he was a lawyer. In fact, people like Professor Gopkumar or me or Ajit have a privilege that we, love physics and astronomy, string theory, mathematics, and we are paid to do that. But Fermat did not have that privilege. To earn his living, he had to spend time being a lawyer in this town in southern France, Toulouse. So whatever he did was in his spare time. Okay? So he didn't write many papers. He would just keep writing letters. He would scribble notes in the margin of books. And of course, people later on found out that he had actually founded number theory. A lot of you would have heard of the Fermat theorem that you cannot, Pythagoras theorem is fine, 3 squared plus 4 squared equals 5 squared. But with integers, you can't do it with any power other than 2. So he conjectured that. And it took only 400 years to prove it. Okay. Then some gambler friends of him asked him, why does this happen more often? Why does that happen more often? So he got together with his friend Pascal, and they created the modern theory of probability. Analytic geometry, we usually think of Descartes, definitely the founder, X and Y, but Fermat was also there. Calculus might be a little bit of a surprise. So let me tell you a little bit of a personal story. I happened to attend a conference on gravitational lenses in Toulouse. Okay. Of course, obviously I had to mention Fermat and his principle. And then we were taken in the evening to the town hall of Toulouse, because after all, he was an important citizen. And there was a statue. And in the bottom of the statue was written, here is Fermat who did this, and invented differential calculus. The Englishmen were very unhappy because they thought that Newton invented calculus. The Germans in the conference were also unhappy because they thought that Leibniz invented calculus, right? And actually, Fermat almost invented calculus. He invented the theory of maxima and minima and did something like differentiation. But as an Indian, of course, I knew that none of these people invented calculus. It was invented about 100 years earlier by Madhava in Kerala, but that's a different story. Okay. So how did Fermat manage to do all these things? And the answer is he believed in doing things in the least possible time. Okay. So many of you would have heard of the principle of least time in optics. Okay, and actually, to be fair, he gave this principle for the case of refraction because a Greek person whose name is sometimes spelled as hero, sometimes spelled as Heron, had already given this principle for reflection. So if you're worried that I'm telling you something very ancient in 1600, I'm going to take you back another 1600 years to this person. We don't know that he really looked like this, but this is one of his gifts to all of us, which all of you know. He also built a steam engine, a vertical axis windmill. So in those days, you could be an engineer, a mathematician. And he gave us a beautiful way of looking at the law of reflection in optics. Okay, so I'm mainly going to be talking about reflection now, and we will move to refraction toward the end of the lecture. In fact, I would request, since I'm using full screen, I'm not seeing the clock on my thing, that I should be warned, especially since we lost some time. So this is the argument. Okay, so this line is the mirror. Right? A is some point, B is some other point. Now, if you wanted to go from A to B, or if light had to travel from A to B, taking the path of least time, first of all, we don't have to worry about time. We can just worry about distance because it's only traveling in a single medium, right? Namely air or vacuum. So this would be the path of least time. But suppose you asked a slightly different question. The light beam has to go, touch the mirror, and then come to B. For example, A, Q, B is a path of that kind. So which would be the shortest path? Okay. And the argument, geometrical argument of that time, given by Heron, is as follows. He said, let's not calculate AQ plus QB. Instead of AQ, let us calculate A prime Q, which is equal to AQ. And why is A prime Q equal to AQ? Because A prime is the image of A. In this plane mirror, the plane mirror is the perpendicular bisector, and all points on the perpendicular bisector are equidistant from the object and the image. So instead of looking at AQ plus QB, let's look at A prime Q plus A prime B. Now, this is a very silly way to go from A prime to B, right? Because any two sides of a triangle are together greater than the third. So you should just go direct from A to B, and wherever that line intersects the mirror is the point where the reflection will take place according to the principle of least time. Okay. All right. So you've got the point P, which lies on the straight line. And how does this give you the law of reflection? Well, because the mirror is a mirror, this angle equals this angle. And because we have two straight lines intersecting, this angle equals this angle. Sorry, I didn't give them names, but this is really basic. So now this is 90 minus the angle of incidence. This is 90 minus the angle of reflection. And there you are, I equal to R. Okay. However, this is not the whole story. Okay. Because we know, that's why I put this question mark here. Is this really the least path? Because we know that this condition I equal to R would hold even if it was a curved mirror. Okay. Then this geometrical argument will not work. We need some other kind of argument, which we will come to. Okay. But I want to quickly convince you that if you have a curved mirror, this may not be the shortest path. So I have three cases now. Can all of you see this? This is my drawing of a semicircle. Okay. Those of you with keen eyesight will realize it's not a semicircle. And the center is somewhere here. But the point we're interested in is a point inside the center. We said a light ray travels from A to B, right? In this case, I'm choosing A and B as the same point, just to illustrate or to explore whether we are dealing with a minimum, a maximum, or anything else. Okay. So you start at a point which is inside the center. Now, our ordinary law of reflection tells you that you will go in along this axis, hit the mirror, come back, and normal incidence, you will come back from A to B. So that is according to the law of reflection. Now, is this the shortest path from here to the mirror and back? It looks like it. Yeah. And if you think a little more, if you want to explore whether this is the shortest path, draw a circle centered on this point. I haven't drawn it, it'll clutter up the figure. That circle will have a smaller radius than this circle because we have placed it here. So that circle will lie inside. So that tells you that if you go to any other point, the distance will be more than this distance. But now the same argument will tell you that if I pick my point A, which is both the source as well as the receiver of the light, I put it outside the center, right? So again, the law of reflection tells you that this is the ray which bounces off the mirror, comes back. And now we can draw a circle centered on A, which has a larger, a larger radius than our mirror. So that circle will now lie outside the mirror. So that means if you go from A to the mirror, it's actually a shorter path than going to this point. And anyway, even looking at this figure, you can see that this is shorter than this. So it really means that the principle of least time should not be called the principle of least time. It should be called the principle of maximum or minimum time. Okay, doesn't sound so nice, but there you are. And finally, here's the third case. Let's put the point A at the center. And now you notice that either the law of reflection or the Fermat principle does not give you a unique ray. You can go from here to this point, come back. It's a normal incidence. But because you're in the center, you can go anywhere and come back. You're still a normal incidence. Right? And all these paths are equal because you're at the center. So this is a case where the function, when I say function, what is a function of what? The path length, which is equivalent to the time, is a function of the point on the mirror where the path goes and comes back. So here the function was a minimum, here the function was a maximum, and here the function is actually a constant. But actually, the Fermat principle is telling us something very interesting here. Because what have we done here? We have formed a perfect image of A back at the same point, okay? And what this tells you is that when you're dealing with the case of imaging, number one, multiple rays from the source will end up at the image. And number two, all those rays will have the same path length. Right? And that, I don't know whether that is normally told to you in high school or in college, but that's a direct consequence of the Fermat principle. Okay? And again, I'm not abandoning this topic. We'll come back to it. Okay. So what should we call this principle now? It's not a principle of least time. It's not a principle of most time. It could be a principle of constant time. So the answer lies in a mathematical concept called stationarity, okay? which maximum, minimum, constant are all a particular case. So I want to explore. So really the correct name for Fermat's principle is the principle of stationary time. So as a general mathematical principle, we have path length as a function of the point on the mirror. But let's just say that we have something which is the function of something, okay? Something else. And then you make an epsilon variation in the path. And then if you are at a maximum or a minimum or a constant, then you don't get an epsilon variation in the path. You either get no variation or you get a much smaller variation. For example, at a maximum, you can easily see, and we'll draw a sketch soon, that the variation is only epsilon squared, okay? Actually minus epsilon squared. So that ensures that whether epsilon is positive or negative, the value becomes lower than the value at the point we're interested in, right? Of course, it could have higher powers also. So this is the notion of stationarity, that the first order variation in the path will cause a second or higher order variation in the time taken to traverse that path in going from the source to the second. And this is the argument that Fermat used. So Fermat created the theory of maxima and minima, and then he realized that in order to make this theory work, I have to look at the coefficient of epsilon, and at the maximum or minimum, it should be 0. So he calculated the coefficient of epsilon, right? And that's today what we call the derivative, right? If you look at the change in the function, where x changes by epsilon, how much does the function change? What's the coefficient of epsilon? That's the derivative. So he worked out the derivative for any function that he was interested in. But he didn't make a song and dance about it. He went back to his legal cases, his number theory, his probability theory, right? So in a sense, he does deserve credit for the differential calculus. So I now want to give you a couple of examples of stationarity, which are purely geometric, but they're interesting in their own right. Right at the beginning, I said we all know that a straight line is the shortest distance between 2 points, right? That's why a light ray in vacuum with no mirrors travels in a straight line. However, suppose someone asked you to prove it. How would you prove it? So look at the upper diagram, right? Yeah. So here is point A, here is the point B, and the dark blue line is the straight line which joins them. Now what we're going to do is to take some other path, right? And then this path differs by some epsilon. Going from here to here is proportional to epsilon. The more formal way of saying it is, let's take some function f of x. The shape of this path is given by f of x, except that we will multiply this fx by an epsilon, so that when epsilon is 0, you come back to the straight line. Yeah. So we have a path length. Now the question is, can you have a coefficient of epsilon? And there's a very simple argument which tells you that you cannot. Take this path. Now you make this a mirror and reflect it. Okay. It's a plane mirror. So this is identical to this. It has the same path length. So it means that whether epsilon is positive or whether epsilon is negative, the change in path length, there is definitely a change in path length, but the change in path length is the same. Now that can't be. If there was a term with a coefficient of epsilon, then for positive epsilon, the path length would go one way, and for negative epsilon, the path length would go the other way. But now I'm telling you that for positive and negative epsilon, the path length is the same. So therefore, we have a situation of stationarity. The coefficient of epsilon vanishes, and you have either epsilon square or maybe other terms. We don't know that, but definitely not epsilon. So this is, if you like, a geometric way of seeing that the straight line is the shortest distance between 2 points, but it's not purely geometric. You need this interesting concept which goes back to Fermat and perhaps earlier, in fact, to the Indian astronomers. Right? Now I'm going to use this to help you in your air travel. That's a practical application. So here's the Earth, and here's the equator. And all of you know that the equator, I mean, I'm not showing you the equator as a circle because I'll have to look from the pole to do that. And the equator is the intersection of the sphere with a plane which passes through the center. So it's a mirror plane, right? It's because it passes through the center. So you can use exactly the same argument. You are going from some point on the equator, need not be opposite points, some point on the equator to some other point on the equator. And the shortest path is going to be going along the equator. Now, suppose you're not at the equator and you have 2 points. Then, well, equator is nothing sacred, right? What you should do is draw a plane through those 2 points, going through the center, just like the equator. And then the shortest distance will be the intersection of that plane with the sphere. So that is what is called a great circle. You will agree that the equator is the biggest circle you can draw on the sphere. And the other circles, like the circles of latitude, are actually smaller because the radius is smaller. And why is the radius smaller? Because this circle of latitude, which I'm again showing you only a side view, is the intersection of the sphere, but with a plane which doesn't pass through the center. Right? It's a axis, but it doesn't pass through the center. So this is not the shortest distance between these 2 points. The shortest distance is a plane which goes through these two and cuts through. It doesn't look like this on this figure. So in the break, you can take a lemon or something like that and take a knife and check this. Or if you don't want to destroy the lemon, you can stretch some pieces of string on the sphere. Okay. If we had a live lecture, I would have demonstrated it to you. Now, what's the practical application? Suppose you're taking a plane from Abu Dhabi to Los Angeles, both of which are reasonably southern cities. And suddenly the pilot tells you that we are now over Greenland. You might think that he's taking you by a longer route, but he's not. right? So, by the way, we've set up a small problem in the problem session, both based on this and on this. So, I leave that as a small surprise, which my colleagues in the TA group will tell you. You can make interesting problems based on this and this. So, that's the notion of stationarity. Now, let me just check how we are doing. Time. Oh, we have a decent amount of time. So I can tell you something. I think the reason is that when you have slides, you go very fast. But I hope it wasn't too fast. Yes. Anand Balivada raised hand. Yes, sir. Unmute yourself.
Yeah. Hello, sir. I just was wondering whether this argument of, like, how does this argument of intersecting a plane with the surface to get the shortest path along the surface, like, generalize to perhaps things that aren't just spheres, maybe like ellipses or even things which aren't symmetric?
And generalizes using a lot of maths. and yeah, so a good question. No simple answer. So in fact, very great mathematicians have, the shortest paths are called geodesics, and geodesics on the ellipsoid, which is the problem that you studied, was studied by Jacobi. And it has a lot of application in the theory of gravitation. Ajit would be the best person to tell you about this. So I will stay away from that. So good question. So if you don't have symmetry, then you have to work harder. That's the answer. So a little bit of the history of the law of refraction. So we all know that this is called Snell's law, right? Snell is the person in Holland. Sorry, I couldn't get a high resolution picture of him. Willebrord Snell. 1620 is roughly when he found this law of refraction. Again, there's a little bit of nationalism here. If you happen to grow up in France or even in Pondicherry, perhaps in the early days, you would have been told that the law of refraction was discovered by Descartes. And the same person who gave you analytic geometry, and the philosophers know he also gave you the mind-body problem. Important man. In fact, I would say in some ways he's the most important person for all of us, because if we didn't have graphs to draw, we wouldn't be able to communicate. We wouldn't be able to figure out anything. Anyway, he actually did it later, but Mr. Snell did not publish. Okay. So who is right in this debate? And the answer is neither of them, because maybe about 600 years earlier, the law of refraction was very clearly stated by this gentleman. And where was he? He was in Baghdad. His name is Ibn Sahal. So we could call it the Sahal law rather than the Snell's law. Except actually Sahal is the name of his father, because Ibn Sahal means son of Sahal. So we are really honoring his father. And you may say, look, how do I know that this person really discovered the law of refraction? Well, if you can read Arabic, then he said it all here quite clearly. I'm told by scholars who have looked at this manuscript. And it's not that this is a lost manuscript. His successors read it, and they extended the debate. And one of them is even supposed to have made spectacles for himself. So this is just, we really have to be very grateful to this flourishing science and mathematics in Baghdad, because that is the route. Baghdad, Cairo, many places. That is the route by which a lot of the Indian discoveries carried on. So another big name is Al-Khwarizmi, mathematician, and so on. Never mind. So I just thought I'd give you this little bit of history. And then here is really Fermat's contribution, okay? That least time not only explains reflection, but also refraction. And now we have to make a distinction between path length and time. If you're in air, the conversion factor from path length to time is divided by the speed of light in air, 3 times 10 to the 8 meters per second. But the moment you enter water, let us say, you have to divide by, it takes more time because the speed is less. Okay. So there is a source somewhere far away here, and there's a receiver far away. Why am I saying far away? Because this is the ray, incident ray, this is the refracted ray, right? And we are going to use the principle of stationarity, okay? So we're going to displace this point where the ray meets the surface a little bit, okay, by some epsilon. So because epsilon is so small, the two lines joining these 2 points to the source are almost parallel. And we want to compare. Now, it looks as if this is obviously longer, right? But once you enter the second medium, you can see that now this has to traverse a longer path and this traverses a shorter path. So really the time taken to travel from here to here should cancel the time taken to travel from here to here. But this is a longer path and this is a shorter path. So how can the time cancel? Because the velocity is slower here and the velocity is greater here. Okay. So here's the calculation. What is this extra path? Okay. It's epsilon times the cosine of this angle, right? By the way, I've drawn this as a straight line. Strictly speaking, it's the arc of a circle, which is centered on that source. And that arc would be perpendicular to both these lines. But when that point is very far away and epsilon is small, we are approximating it by this line, which is perpendicular to these two parallel lines. Again, if you don't like these approximations, we have set up a nice problem where you can do an honest calculation with calculus and convince yourself that this is correct. Yeah. So epsilon times the cosine of this angle, which is usually we measure angle of incidence with respect to the normal. So this angle is 90 minus I, cos of 90 minus I is sine I. So this is epsilon sine I, and this path is epsilon sine R. And the two things which have to cancel are epsilon sine I divided by V1. Yeah.
Rajaram, there's a hand up by
Yes.
Arsh Chutalia.
Yes. Yeah. So my question is, how did they know that light travels with different speeds in different
Okay. Will you wait a few minutes? Okay. A good question.
Okay.
So that you have really anticipated, right? So you have epsilon times sine I by V1 is the extra time, which this one loses, but then it gains, right? Sine R by V2. Huh? So the principle of stationarity tells us that the coefficient of epsilon is 0. So this is, so therefore you get a condition sine I by sine R is V1 by V2. Now Fermat knew that sine I by sine R is greater than 1. So he therefore deduced from his purely theoretical principle that light has to travel slower in water. No one had the technology to measure it, right? So that is brilliant. And it's even more brilliant because his great rival who was sitting in Paris, Descartes, believed in exactly the opposite, that light travels more rapidly. Okay. And of course, he had an explanation based on a particle theory of light, that if it travels more rapidly, it will be bent toward the normal. And of course, some years later, Newton also believed that light travels. So Fermat really, based on his principle, decided. He is a mathematician and a lawyer. He was not going around measuring the speed of light. I always tell my optics class that if you want to make a great contribution to optics, number one, you have to be born in France. Number two, it has to be in the 19th century. And number three, your name has to begin with F. Okay. So you have people like Fizeau, Foucault, Fresnel, Fourier, all of them. Okay. And it's Foucault who actually measured the velocity. So in a sense, Fermat was vindicated. So this is the principle of least time. Now in the problem that we have set up, we have made it a little more dramatic. So this is a beach and people are bathing here, and there is a lifeguard here whose job is to save them if they are drowning. And the lifeguard can run at some speed on land and 1/6 of that speed in water. I got that number of 6 by dividing the 100-meter swimming record by the 100-meter running record, right? And the guard has better reached this drowning person in the least time. So it's the same problem, right? And so there are lots of interesting things you can think about in the problem. First of all, given actual numbers, what should the guard do? Of course, if the guard spends a lot of time calculating using Snell's law, then the person may drown. But that's a practical matter. Let's not worry about that. But what happens if the guard is here? What happens if the guard is also swimming and then has to rescue someone? So you can have some fun figuring all this out. So I think I've reached the stage that I wanted to reach. So let me stop sharing. And I don't think we certainly have time for some quick questions. I'm happy that a couple of people asked. More of you can ask now. And when we resume at 11:30, again, we'll give some time before you break out into these groups. Okay. So.
So anybody who has questions can raise their hands by going into the participants tab and clicking on raise hand. So please feel free. Sorry, I think Siddharth raised his hand first, so let's go with him first. Siddharth Jain, please unmute and speak into the mic.
Good morning, sir.
Yeah.
Sir, I wanted to ask that the principle of least action we have derived here. So, is it really a principle, means a fundamental principle of nature, or the things have more fundamental principle, like we do different kind of mechanics we have where force laws and all that. So, are those the most fundamental principles of nature, or this is the most fundamental principle? It may be that this is just means consequence and not the way nature works everywhere.
Okay. Absolutely great question. One reason why Descartes and others did not like Fermat's principle is they said, look, how can a beam of light have some intelligence to figure out where to go and which is the least path and all that? So let me give you a quick answer. In optics, it's not the fundamental principle. The fundamental principle is based on waves, and it's based on so light. Actually, when you talk of waves, many paths are possible. We will come to that.
Yes, sir.
And then let me just give you a preview since you asked this question. When you have a least path, then the neighboring paths differ from it in length by epsilon squared, which is a very small quantity. Therefore, they, in terms of the number of wavelengths, all these paths are almost equal, so they interfere constructively. So that's the deeper answer to the principle. Until then, people did worry about the philosophy of both the principle of least action. So this is the principle of least time in optics. Once you understood that light really consists of waves. So then people should have jumped on the principle of least action in mechanics in 1820 and said, there must be some waves underlying these particles. But they needed experimental evidence, and that came only much later, and quantum mechanics was born. So, so this question has actually unmasked my future plans, but yes.
Yes. Sir, so if there is some bigger particles which have a very low wavelength, then there should be a difference in principle of least action, means that should not be followed in case of particles which doesn't show much quantum behavior.
No, in fact, it's the other way around. The shorter the wavelength, the better the principle of least time or principle of least action works. That is, that path starts dominating. But sorry, this is taking us a little beyond this lecture or perhaps even this course. But I would be happy to give you things to read and so on this subject. And there was one more question from Pranav. Pranav, now let's give Pranav a...
Yes, Professor. I just wanted you to revisit your statement about the reflected rays of an image all having the same path length or the time. Would you just revisit that concept?
Okay, so I am going to revisit that in the next lecture. So what I will just tell you is that I gave you the most obvious example, that you are standing at the center of a circular mirror, and therefore you send a ray in any direction, it will hit the mirror normally and come back to you. And by the way, this is best demonstrated in acoustics. If there's a circular wall, you stand at the center and start talking, you will deafen yourself. It's a very interesting experience. They should be there. But by the way, if I want to go from point A to point B, I can ask you, what is the set of points such that, suppose I call that point P. I want a point P which moves around so that AP plus PB is a constant, and that is an ellipse. So I've given you a little more hint. Then ellipse will perfectly focus rays from one focus to the F1 to F2. Thank you.
We normally use our solar panels which absorb sunlight, and solar panels are the most common way of harnessing solar energy. But what happens in solar reflectors is, I guess, it concentrates all of the solar energy into a single focal point, right?
Not a single focal point, but an area. But we will come to this. Huh? So you have to be a little patient. Solar panels, you would not want to do that because your silicon will not, if it gets too hot, it will not work. But suppose you want to melt a metal or you want to generate steam, solar energy can be used for those, or conduct some high temperature chemical reaction. All that you need to concentrate solar energy. And I emphasize concentration is not the same as focusing because the target is of finite size, not a single point. And because the source is also of finite size. It's a sun which subtends half a degree. So please be patient.
Okay, sir. Thank you.
So there's a question from a YouTube viewer which Ajit has put into the chat, which asks, are these least action principles consistent with quantum theory unless we don't reach path integral formulation?
No, we will not reach the path integral formulation of quantum theory. We may reach a path integral formulation for optics. We may.
So I think the question is, are these least action principles consistent with quantum theory? And that's the main question.
Yes, and the person who really showed that is Feynman. And I think the questioner knows that because he used the word path integral. He or she has used the word path integral. So Feynman was the person who connected least action principles to quantum mechanics through this very intuitive idea that paths which have a similar number of wavelengths will interfere constructively.
So another question is, what kind of light source did the early optical physicists use to describe the properties of light?
Many of the experiments, Newton's experiments were done with the sun. And I think even the young experiments were done with the sun. In fact, C.V. Raman, when he moved to the Raman Research Institute, did not have electricity for 4 years, but he conducted his optical experiments with sunlight and his assistants and students. So sun was a favorite source. You could put filters if you wanted a smaller range of wavelengths. I'm told that Young, when he actually used a candle because to see these fringes, he needed a very, very dark room. So,
okay.
Fizeau used some kind of arc lamp to measure the speed of light. By 1817 or something, arc lamps were available.
One more question from YouTube is, could you explain the diagram on moving between 2 points on the spherical surface of the Earth once formed?
Okay. No, instead of, let me try do a little bit better. Are people seeing this whiteboard? So let me see, there is some technology here whereby I can probably draw a nice circle. So now I'm going to not take a side-on view. Imagine that we are looking at it from the North Pole. So North Pole somewhere here, and these are the circles of latitude, right? Something like that. So here is the example I gave, which is connecting some Abu Dhabi to Los Angeles or something. So what one is really saying is, I can also, this dotted line is the back part of this circle of latitude. Yeah. And you can see that it corresponds to a plane which doesn't pass through the center, right? The equator is slicing the sphere with the plane passing through the center. This one doesn't pass through the center. So it's actually a smaller radius circle. But I'm saying going from here to say here, this is not the best path. By our whole symmetry argument says that the shortest path will be one where you have a plane going through the center. So from here to here, you imagine cutting it, and you will actually have, let's do some high tech. We'll have a path going like this, little bit to the north. And if you want to go further up, you will actually end up in a path something like that. Yeah. So that's why you go over Greenland when you go from Abu Dhabi to Los Angeles. Hope this helped. Okay, nice to have all these questions, and maybe I should have mentioned that you do not have to take notes of anything which is on the slides, because the slides are available in this place called Moodle, which all of you will get accounts or have already got, and the problem sheet will be available. Some solutions will be available after some time when you have had enough time to think about the problems. But by all means, keep notes of questions. Please do that.
There is also one last question on whether there are any wave optics formulation of the gravitational lensing.
Yeah, strictly speaking, wave optics does need, I mean, any optics should first be done with wave optics. In fact, it should be done with quantum optics, right? That's the accurate description. Wave optics is an approximation, and ray optics is a further approximation to wave optics, where you don't look at all paths, but you look at the path of least time. Or in the case of gravitational lensing, multiple paths. So yes, but when you actually work out whether you can see these interference effects and so on, except in very rare cases, you don't. I do see some papers saying that gravitational waves, if they undergo gravitational lensing, will need us to look at the wave optics aspects.
That's exactly, yeah. There is a possibility of observing wave optics effects in gravitational waves, which is likely to be observed the next 10 years or something.
And they are more monochromatic. You know, that the other reason why you sometimes don't observe fringes is because the source is not monochromatic.
So this is just because the gravitational waves have much lower wavelength, and you have objects
longer.
Much longer wavelength. Yes, yeah, and there are objects whose characteristic length scales are comparable with the wavelength of gravitational waves. So if there are no further questions, let's thank Professor Nityananda for this wonderful introductory lecture.